logistic regression at it, right? So throwing these more complex methodologies that we're gonna be working on, like trees and stuff, what's the point? They're not likely to improve the performance. If it's a simple, fairly separable or, relatively, by feature, by coordinate system.
Right.
So I'd say you need something that has at least enough dimensionality to be of interest and of merit for the classification and feature reduction, right? So feature selection methodologies. Because if it's so simple you can do it with linear regressions, or simple, i.e., straightforward enough that you can fit one thing to another thing with a degree of accuracy, then you don't really have enough features to throw a feature selection model at it. So I think there's going to be, I would say, largely something simple, straightforward, relatively easy to work with. You can pull from your ISLR2 or mass data sets if you need those for the linear regressions, but do something different than you did with your first linear, of course.
Right.
But as far as the classification paradigm, focus at that point in time would be to find something that's significantly more complex than the linear, but not so complex as to be, out there, not a huge data set. So I gave you a list
like
of
3
things
or
that I
4
think are good.
dimensions or features.
I would say 20 or 30 usually is what I recommend for the feature selection, because when you think about feature selection, subset selection, dimensionality reduction, if you want to get the most out of it, you need enough dimensionality to vex a relatively complex, classification system, which we know neural networks, for example, are complicated enough that they can solve a lot of the problems that we've been dealing with, with sufficient complexity. They should be able to hack it. But we're not going to be doing neural nets, we're going to be doing SVMs, which are only just slightly lower than, excuse me, than like a MLP, multi-layer perceptron. I haven't used that term so far, but that is another term that gets used frequently, but we just typically call them neural networks overall. You need something?
Oh, it was just unplugging the computer.
Oh, that's your computer, okay, I was wondering whose it was. Would have been fine if you left it.
Yeah.
You might need it, right?
Yeah.
This is the one room that really stinks because there aren't any plugins on the desks.
Right.
They've been talking about reworking this room, but the problem is that the way it's set up with the staircases.
Can we get them to rework Royal Hall Room 104? Can we get some of these put in there instead of those little
I'm in 201 Hague.
God, I hate
For my
those
other
desks.
section, my Tuesday, Thursday is 201 Hague. That classroom has to be one of the worst, and it's used fairly frequently. All right, so thinking about this, I've actually came across a topic that I wanted to discuss with you guys that I found a paper on, and I think I might actually assign you guys to look through this paper. I might assign you guys to look through a few papers as we get close to the end of the semester, because once you start thinking about things in a little bit more complexity with regard to how this stuff works in the natural world, one of the newest sort of challenges that we've been facing is biological neural networks are not, they're not as constrained, or excuse me, let's flip around the other direction. Artificial neural networks are not as constrained as actual biological networks, right? So the biological network's constraint runs in more than just structural complexity, right? So technically the brain is very structurally complex. If you were to think about the brain with respect to how it operates as a neural network, it would be, it's trillions of nodes, effectively, because it's got a lot of recurrent stuff and feedback-driven integration. So you have billions of neurons with trillions of interconnections over that system. Effectively, the potential interconnectivity between the neurons in the brain is like just one step, one magnitude over what is effectively calculated as the mass coefficient of the universe. right? So if you looked at the cortical connectivity of neurons in the brain, and you said all of the different recombinations of connectivity in those neurons, it's about 10 to the 80th power. Rough combination of neutrons and electrons in structural matter is about 10 to the 79th, according to our current estimates. So it's slightly more complex than anything you could possibly imagine with regard to a system of moving elements. So if structure and attachment and recombination, if form follows function, then the way the system is put together, how it's arranged spatially, how the things communicate with one another, is in fact how it works, right? It's not just the components and their operation, it's how those components are arranged. So one of the things that they've been working on is this idea of implementing a new performance metric, which is to constrain the amount of neurons or the number of neurons that are activating at any given time as a result of some input. This is the idea of energetics, right? If you think about it and you say that the human brain doesn't want to burn all the energy that the body has coming in because that's not efficient. We would die if it just ran all the time at full speed. That's the reason why a lot of people say you're only using 10% of your brain. That's 10% of your brain at any given time, right? That's not saying you only use 10% of it structurally. It's just saying at any given time, only 10% of it is active. So that 10% changes, which portion of it is active and how it is active changes over time. The key consideration that they put forward here was if we add the constraint to say that you not only have to be accurate, but you have to be efficient, they're getting closer and closer to building systems that can run on less power and require less total resources to accomplish the same level of operational efficiency, right? The brain is effectively rewarding, reinforcing, adjusting the weights, using the back propagation mechanisms of regression. It is taking that information and it is rewarding efficient sequences of neurons and saying they can continue to operate, but inefficient sequences of neurons get clipped out, right? You say, hey, you're not necessary. You're not contributing to the global positivity outcome. You're not making an improvement. So similarly to how we were working with regularizations in the past, right? You remember we had our L1 and L2 regularizations. We can imply regularization with respect to the system by forcing the system to stop before it becomes too efficient, right? Because there's a now balanced multiple efficiencies. We say this is an efficiency with respect to error metrics, that is the quality at which the accuracy is working. But what happens as you get further and further this direction? You need more and more neurons to participate in that process, right? So to overfit, we have to what? We have to over-parameterize the model with respect to the number of dimensions or the complexity of the internal nodes, the hidden interconnections of the nodes. So if we say structurally we have gotten to the maximum amount of complexity, interface complexity, without suffering a diminishing return on the level of computational output, right? The generalization is a reward for getting rid of or limiting the increase in structural complexity of the system. Now this is similar but not identical to the process we were talking about with respect to the increase in complexity of just increasing the factor of the equation of linearity, right? So we said, what do? We use k-fold cross-validation, we increase the order of the coefficients, right? You have a second order, third order, fourth order coefficient. So by adding in those additional nonlinearities, we get a more complex shape. We can model things to a higher degree of accuracy. In that effect, we had the option to be able to shape the model totally constrained and saying we were taking into consideration all of its computations. However, we don't really have that control over a neural network. A neural network has whatever degree of complexity it has based upon its interconnectivity. If it's fully connected from layer to layer, that's how many weights it has. Without doing something more radical, like trimming away connections between the elements, the only thing we can do is to try and stop it before it becomes it memorizes too much of the information. right? There's a weird thing about this is that neural networks are usually trained in loops or in cycles that we call epochs, right? Or epochs, depending on how you pronounce that word, a couple of different pronunciations. The idea is that an epoch or epoch is a period of time that is characterized by one full cycle through the entirety of the training data set. So if I loop through and have included all examples of the training data set at least one time, I may have adopted or adjusted the weights in the system several times through that epoch. I might do it on a individual batch level, right? I might do 10, if I've got 1,000 samples, I might do 10 or I might do 100 at a time. And then I'm gonna look at those 10 and I'm gonna back propagate and adjust the weights, adapt to those, and then try the next 10. Do the same thing, do the next 10, right? So by the time I've gotten done with one full sequence of the process, I should have seen all the samples and I should have adjusted based upon the characteristics of all the samples, right? Everybody got a chance to participate in the back propagation of the error, but I wasn't trying to fix all the error at once. That matters because if I was trying to fix all the errors at once, the underfitting, overfitting dilemma would only be fixed on what? The number of nodes in the connectivity of the network. Because if you went through and you back propagated all the errors simultaneously in the system, you should get an ideal output for that relationship. But why is that hard? Why is it difficult? Well, because the bigger the error is, let's say summationally the larger the error is across multiple samples, it makes it more difficult to determine how well the model is doing at characterizing a given subset of information, right? If you do the global error, effectively the RSS of an entire data set in a neural network, what are you going to be doing? You're going to be changing each of the weight values by a lot every single time you try to do that. So by narrowing our scope and looking only at a few examples at a time, we effectively create a variety of different subsets of information. We're kind of K-folding in the effect of saying we're building different interpretations. But every little snapshot, every little small window in the batch gives us a little bit of new information about the system, and it attempts to stop the system from characterizing only on the small amount of examples that it can see at any given time. Since there isn't an overlap from batch to batch in most training environments, each of those is a snapshot of time or kind of a snapshot of a random subset selection. By adapting and compensating only to that subset, you're able to increase the amount you can learn from that group without compromising the overfit, right? Because you're not memorizing for that group. Because the moment that group is out of the picture, what happens? Now you have to maximize performance for the next group. So you can't keep all the information you had from the first group. That stops you from memorizing, right? I say you have to generalize because you can't see everything at once. This is similar to a masking process, if you know what masking is in terms of like an image mask, where you're sort of like looking at a sheet of paper with a bunch of holes punched in it, right? So you put that sheet of paper over top of an image, and you can see what's under it, but not all of it. So by only being able to see some of it at any given time, you stop the system from memorizing the full structure. You make it try to find connections between the elements that it can see. By doing that process over and over again, and masking and only allowing certain image characteristics to be viewed at any given time, we can improve the performance. All right, this is where I was talking about the mini-batch mechanism. One of the reasons why this process has been taken on within larger sets is because the computational loss over the entire training set to perform a single parameter update for a large image would be massive. There are approximately 14 million images in ImageNet, right? Each of those is, when rescaled for operational vanilla deep learning, is about 256 by 256. So that's a huge array of information you're having to process. You have to do 14 million of those before you can do any kind of learning. That's not workable, all right? So we need to learn on the fly. We need to learn a little at a time. So that's also another reason why the mini batch process, looking at a small subset of the images or a small set of the inputs of a system, is an improvement in performance over the whole set regression process we've been taking on in the past. Another cool thing about this is if you're training these systems in real time, in real life, we can actually get past a problem that's been plaguing us and some of our issues, right? Which is previously we had to have the whole data set. We had to have it all the information extracted out of it and everything normalized and categorized. Now we can just watch for a minute, right? And then we can process that minute of information, run the regression, do the update our outputs, and then watch for another minute. If your previous suppositions are enforced by your subsequent observations, right, your accuracy is getting higher, that's good. You're reinforcing, you're going to do positive, constructive increases in informational characteristics. The difference between what is called offline and online learning is what I'm talking about here. I know I'm throwing a lot of terms at you. Some of these I will require you to know, some I won't. I'll try to give you like an exact set of terms that I'm going to be covering in any kind of assessment. This probably we'll probably have spent more time on this than will seem like it's sort of reflected on some of the assessment work, because while I consider this important, I consider this a lot of information, and it is technically delegated to its own class, but I think it's so important now, like neural nets are such a key factor in a lot of the construction of machine learning models in the world today, that you guys have to have an understanding of it. Even if you choose not to take, deep learning or adaptive systems, you should understand this to be able to converse with people who are doing some of this work in, the industry, right, where you might end up in, a short period of time. So the idea of the batch-driven system is actually a reflection of the idea that in real biological systems, we don't have the opportunity to keep track of all the inputs we had previously, right? We don't have a tape loop that we're running. Technically, we don't have like a full one-to-one tape loop of everything running in our brain. So we can't keep a windowed aperture of previous inputs and keep expanding the window of aperture of the previous inputs. What we're actually going to have is we're only going to have our short-term memory, the capacity of short-term recall that we're able to pull from. So that short-term recall will be a first on, first off buffer, FIFO buffer, right? So new inputs coming into the system, old inputs drop off. So the window of the batch system, the max window of the mini batch, becomes the local memory of that FIFO buffer, right? You can keep adjusting your system, you can keep learning and improving over time. The information you gain from the past examples can be utilized and carried forward, but it's carried forward in the weights. This is an important aspect. It's the one that took me a long time to really get. The model's interconnectivity is a picture of the data it was trained on, in the same way that a line is a picture of the data it was trained on. Once you model it, once the model starts to converge, the model is a form of memory. It remembers the most significant, the most correlated elements of the inputs that it had previously. So your memory, your behavioral transformation in your life based upon your previous events, you are the product of that data set. You don't need to remember it because it is part of you. You have integrated it into your neural connectivity. You now have a model of your entire life experience. Adjusted, subtly adjusted, and adaptively adjusted, right? Not everything gets retained, but it's most of what was there already, right? The structure gives you something to work off of initially, so that when something new comes along, when you're real young and you don't have a lot to compare it to, think about it this way. Real young, you don't have a lot to compare it to. One experience can be very formative. Why? Because its error, its weight does what? Propagates back heavily and adjusts a lot of your perceptions, your connectivity, your ideas of how these things are working together. But as you get older and your weights are more established, then one individual event is going to have what? Your learning rate is going to go down. Your adjustment, how much you're going to take that individual event and try to apply the entirety of your understanding of the universe based on it, is going to change. We understand as children, we start off doing this. We drop things and we see what happens, right? Now I understand physics. A baby understands physics, they understand gravity. But not in a numerical, computive way, but in a modeled call and response way, cause and effect way, right? So creating that connectivity is the long-term goal of these networks, is to retain information, and the information structure becomes integral to the output. Now this matters, I know I'm not getting through some stuff on slides here, but we'll get to them. This matters for a topic that I was planning on covering with you guys a little bit, but have you guys heard about this concept of like data transparency and data security in machine learning? This idea that like a machine learning model, large enough machine learning model can actually be a security threat because your information can be leaked. So if the model is complex enough and it's adapting to the input that it has, and your data, you'll say your behavioral data is in that model, after a while that model becomes capable of basically reconstructing its inputs. Because if it fits almost to that maximum fit point, it's created a model of you. So if it's called upon to process information, or if it's run in the reverse order, it can generate potential outputs from potential inputs. So the idea is that since the model is the product of the data set, that the model now contains some of the information that was in the data set. So how do you create a system that allows you to obfuscate that such that you're not distributing a model that technically contains information that could be extracted from that model as a result of its known adaptation to the framework of that particular data? It's an interesting concept, right? Maybe you didn't memorize some specific piece of information, but you have a general concept of it. And sometimes in general concept of the connectivity between certain elements is enough to merit that. I would think in an effect of saying something like, you guys know how ChatGPT basically listens to everything you're saying, right? Anytime you talk to it, it knows, like, people can monitor those chats. You signed off onto it. Anybody who works for OpenAI can view your chat history. Now, do you think they can do it? No. There's no way in the world they can monitor that much potential information. But guess what? They still have it. They're also using it to train ChatGPT, right? They take the outputs and inputs and the reinforcement between what you said was a good response and a bad response. They took what you asked it in the follow-up questions, the differentiation between those, how the model adapted to your input. They actually feed that back into the system as reinforced outputs and say, hey, here, learn from this data. So that means your interactions with ChatGPT are as much part of how it works now as the artists and performers and authors that all the books that it was learning from when it started out with. You're contributing to that system, right? There's a song online by a guy that's called The Stupendium. Have you guys heard him? He's a YouTuber. He does video game songs, and one of them is like the sort of cyberpunk, the Arasaka security company from Cyberpunk, and it's all about how effectively corporate America kind of takes over the world in the not so distant future. And one of the last lines of the song is, the supply does not get to make the demands, okay? And it's characterizing you as saying, you wonder if you voted for this, and it's like, yeah, check your receipts. Everything you bought empowered us to be able to control the world. You gave us your money, and that allowed us to be able to take over, right? So what the argument in the end that I'm putting forward here is, we are creating a system, an ecosystem, a data environment where we are all becoming part of the product that large-scale corporations are employing for the construction of models that are distillations of our human work. So we have to be careful about the governance and policies and processes, the companies that we get involved with, and what they do and what we help them do, because we have to think on an individual basis about the ethical ramifications of that data usage And in terms of saying, what do they own? What do you own? What is the concept of mutual effort with respect to the construction and training of the data set model, right? Do they own the data that they're training with, or are they just getting access to it from somebody that is effectively selling it or brokering it based upon you getting a free product, right? You're selling your identity, your behavioral mechanics, your response mechanics in the name of a free service. It's not free, it's costing you a representation of yourself. Okay, I know that's really weird, but I'm trying to go to a high level and give you guys an understanding of that. All right, so mini batching with SGD allows us to continue a localized approximation, so we can keep learning on a local level. So we don't have to wait for huge chunks of input. We don't have to try to process the whole system. We can effectively make the argument that any small localized batch should be largely representative of the entire surface from a gradient provision perspective. And I think if you guys look at this with respect to the idea of making the argument that eventually the system converges to the underlying distributional characteristics is based upon the Chebyshev system and the central limit theorem, right? The idea of a convergence of multiple individual stochastically oriented distributions would each themselves be a reflection of the global distribution, with the weight system doing what? Adapting to the underlying distribution by seeing and integrating information from each of those successive mini batches as a small subset representation of the larger system. So just a sampling theorem perspective. All right, we talked about that as the idea of SGD as being the mechanism for min operation. We've talked about this as well. We were able to make determinations for this. Plateau states, saddle points where you don't have clear information about optimization for outputs. Local minimization, being stuck in a local min as being a very bad state, because if we get stuck somewhere where we haven't created a global maximum return on investment, right? We haven't reached the best performance of the model. Anytime you get stuck in a local state, you can't continue to improve because everything would technically be, you would compromise your performance. So you either have to increase your step size or learning rate, right? Those two things are the same in this case. And even at a multi-dimensional level, right? So you can have multiple learning rates, it's possible. I've seen systems with them, they're very hard to optimize. Or you can have a learning rate that does a couple of different things. You have learning rates that adaptively change in simulated annealing, where you're intermittently flicking the ball, getting a little more energy. Or you can do something like a punctuated system, where we're using punctuated effect for gradient descent. There's a couple examples on here of how the gradient descent model goes from adjustments based upon the previous information. We've already talked about this one. We talked about momentum. We talked about adjustment for the momentum characteristic for coefficient, or effectively modeling a heavy ball rolling down a hill. How much momentum do you keep in order to do the parameter optimization? This matters a little bit more when we're thinking about batch size, because depending on how big the batch is, we might want to change how much we update the weights. So the larger the batch, the more samples we have per any given data set, the more likely we are to extract useful information from it. So we might be able to up our learning rates a little bit in order to get the system to converge. You ultimately always want your model to decay that learning rate. You want it to start off with a relatively high learning rate, taking big steps to try to converge to an ideal minima, right? But then as it converges to that ideal minima location, you want to slow down so that you actually find the bottom, right? Because if you're still taking too wide steps, you can bounce around and even bounce yourself out of those minima. So you have to slowly decay the process of the weight update system in order to be able to adjust for and compensate for the smaller, the narrowing characteristics as we get closer and closer to optimum states. Some of these are just here to show, okay, here we go. So we talked about, I said the regularization system for early stopping was a mechanism to try to stop the system by utilizing mini-batch approach towards overfitting. Say, I can keep the same level of complexity, but if I don't let you see everything over and over again, you can't memorize it. So by stopping early and not allowing you to have more access to samples than necessary, I can stop you from memorizing, right? So I know that memorization is what happens whenever the model starts to get too dependent on the set. So if it's not able to see the set more times than is necessary for it to get everything that it needs out of it, it won't memorize it. You can think about this in the same way as if you were trying to get the general concept of a book, but didn't want to be able to recite that book. How many times would you read it? You might read it 3 or 4 times, right? You get the concept. But if you keep reading it over and over again, what's going to happen? You're going to memorize it. You're going to get so fixed in your head that you'll effectively be able to say, oh yeah, I know what the next section is, right? I know what the next chapter is of the book. I have some books that I've listened to or read so many times that I can virtually tell you what the heading of the next chapter is, or tell you what the character says in the next quote, right? Some people, I'll tell you one of my books I like. It's my guilty pleasure book. That's the Harry Potter series. I love them. All right, I love this series. All right, I listen to them usually about once a year. I've listened to them now probably about like 8 or 10 times. All right, now there's a good chunk of books, but I'm still telling you that if I watch the movies now, I can be like, that's not what happened. Hermione wasn't there. Like that. That's what I'm saying. You're getting your head. You get in there. That's memorization. That's when you stopped with the general concept and now you've overfit. Right? You have exact information about specific outcomes. So how do we stop this? I talked about the idea of masking. Now I'm going to talk about something called ablating. Ablating is when you flat out delete neurons. Okay? These are whole nodes in the network that are eliminated from consideration. We did this previously with the L1 regularization, right? With the lasso methodology. So the lasso methodology allowed us to do what? Minimize the coefficients based upon grad for maximization of output. Those could go to 0. So this regularization methodology, which is called dropout in the neural network space, we drop that neuron out of the network, right? We just drop it out. That is the same thing effectively in terms of its result in it creates a less complex model, and each layer of the network does not see everything from the original input, right? We're now actually missing 2 pieces of information, 2 features from the original input vector. We've ignored these 2 pixels. We've ignored these 2 sensors, right? So the information, let's say that the information about the environment or about the characteristics of the input is characterized in this vector, then we're saying that we have to be able to reconstruct everything that we need to know about this vector from these 3 inputs, sans those 2 that we got rid of, right? So the idea would be that the information is distributed across it and now has to do what? It has to dynamically reroute that information across the network in order to be able to preserve that information. It makes the network have to work harder at getting the information through and creating good representations of the characteristics of the data without it having the risk of overfitting. So by ablating those 2 inputs, I now stop the model from ever seeing any input fully, right? It doesn't get to see the whole thing. So since it can't see the whole thing, it must work with what it has. If there's some variance in the input in that space, specifically variance that would probably lead to error, eliminating this actually improves the performance of the model. The human brain does this, okay? The chemical that does it is called testosterone, all right? Testosterone kills brain cells. It says, you are the weakest link, goodbye, all right? So especially in late adolescent development, the human brain will kill brain cells. Why is that a technically good thing? Well, the weakest cells are doing what? They're borrowing energy. They're stealing from the system and not contributing. So over time, as the brain develops, those weaker cells are winnowed out, right? They're culled from the herd. And the resulting model is more streamlined, more efficient, makes the brain less energy intensive, makes us more goal-oriented, focused, target tracking, prioritization, maximization, okay? It's the hunter and the hunter-gatherer framework of, primitive man makeup that sticks with us today. But guess what? If we can take advantage of it and we can utilize it to further optimize the structure of the neural systems, and females do have testosterone, small amounts. So, and it's produced largely in cortical substructures to do the exact same thing. But with males, especially with the high level of testosterone, males have, there's a lot more cells get killed off cortically than females. They maintain a lot of interhemispheric connectivity that we don't have. So by redirecting the inputs through the mini batch, we can actually create a variety of different pathways in the input, right? So which pathway is active at any given time, or which neural model is active at any given time, we notice that I'm redirecting the information from the original input through the now diminished scale network, but I'm maximizing and keeping the maximum amount of information that I can by this dynamic rerouting operation. You can selectively go in and get rid of any given node within a hidden layer in the network, and the network will be able to compensate for it by doing what? Shunting that information. I can shunt the information here up through this node, right? So if I get rid of this one and this one, I can now push the information into these nodes. Now these nodes are carrying the information that these ones were previously, right? That every time I delete a node, its neighboring nodes now have to take over the load balancing. Similar to load balancing processes in large scale networks like the internet backbones, where they have dynamic rerouting. Networks dynamically reroute in a slightly different way because those nodes can come on and off, right? So when the node can effectively switch on or off, can become a good or bad path. So we have to dynamically reroute them. And in a ablative network, once you get rid of that node, its neighbors take over its load, and you don't want to turn it back on. I'll tell you why you don't want to turn it back on. Is because the weights in the nodes that are still active in that layer, they have now taken over the processing of gradient descent optimization for decaying based upon those weights, right? So if I turn that back on, what's going to happen? Now I'm going to be multiplying the previous inputs by either the old weights or some other input weights. It's going to be hard to differentiate who is making the mistake. The neuron that took on the share of the work of the previous neuron, right? Or the neuron that's been added back in the system. So how do I determine which one is contributing to the error at that point in time? Since the operational workload has been shunted to the new node, it's now the owner of that workload, right? So you don't turn these back on once you delete them. They're deleted, they're gone forever, okay? All right, let's talk for a minute. Probably got about, what do we got, 20 minutes? Okay, cool. We've been talking about this concept of abstraction to get to this point, all right? What's the point of this slide? Well, to compare two things. First is the traditional methodology of machine learning, which is the foundations of the things we've been doing in this class thus far. We would say that traditional machine learning takes the natural continuous world, processes it through a filter, that is the process of feature extraction. This is a person sitting in front of a keyboard, quantifying the informational input from that natural continuous universe, right? This is essentially a discretization of that continuous natural world. And I say it's discretization because even if it is analog values being stored, they're still temporally discrete. I still have to take a snapshot and measure that value at that exact point in time, right? So anytime that I'm digitizing information from the natural world, or even just the process of extracting features, useful information from the continuous space, I'm doing a process we call feature extraction. This is why I use the term feature a lot more than I use the term predictor in this class, is because I was trained in neural networks. This was my thing, so I stick to my vocabulary. But also because of the fact that I think that this is the more prevalent of the two choices in terms of the description of what a specific piece of information is. We say that a feature is something that makes up an object in natural space, right? It is the criteria that that particular object can be discriminated from other objects with. Effectively, we say that whichever of those features that we have chosen does what? It constrains the model. Constrains the model. Because if I give you the object, right, and I tell you to tell the difference between an adjacent object of a similar type, and I say, let's say these two bottles, right? Which features, which pieces of information am I going to use to differentiate those two bottles? They're both clear, right? They're different in height now. Okay? Imagine if they weren't? Let's imagine that those two bottles were effectively identical in every way, except for they contained different liquids in the inside. Now, both the liquids on the inside, to my current assessment, is they're clear. All right? The clarity thereof is quantifiable. Right? How much light can pass through it with a certain degree of diffraction is the characteristic that we would call clarity. Now, I would say those two chemicals make up, they're probably very similar to one another, because they both probably are predominantly alcohol-based, but one of them has a jellification agent in it that is part of the hand sanitizer, right? Everybody's become very familiar with it. And the other one is like a whiteboard cleaner type stuff, so it doesn't need to be gel. You want it to spread smooth. So I would say that there's probably a slightly greater diffractive index in the hand sanitizer, which means that it's slightly less clear. Now, what have I done? I went through an entire set of logical principles to determine what piece of information I was going to use to differentiate those two elements. I've now come up with an experiment that I can perform using a sensor. I can collect data from that natural world object to attempt to try to describe those two things apart from one another. What does the machine not get to do? It doesn't get to decide which of those elements that it's using. It does what I tell it to. It works based upon what I give it, all right? But what if instead, I got rid of this guy? I get rid of the human complexing element, right? I know, we need to replace this human. This is a mean human, as Sam Altman said. Fired and then rehired again? What the hell? Okay? Dude, it's weird anyway. So why do I say that this is good? I am, you know me, I've talked about this before, I don't like getting rid of people out of the equation of data chain, okay? I love people being involved in human-centered decisions, because humans do what? Individual humans are moral, individual humans are ethical, individual humans have feelings and worth and value and see worth and value in other humans. Do data systems? No. Do corporations? No. All right, so we have to keep humans in that cycle loop, because if we don't, we're going to dehumanize the human race. We're going to turn us all into numbers. Right? That's exactly the antithesis of what engineering and science should be doing, because we should be developing things that improve the human condition. And I can see nothing about creating everybody as an individual little widget that would improve humanity, okay? So I don't really want to get rid of this person because I think that their job isn't useful, all right? That's not what I'm trying to make an argument in. What I'm trying to make an argument in is, if this person is still present, they are a filter between the natural world and the machine learning system. What can't it do then? It can never be fully automated, because it will require that human to be there. It also does something that is really kind of bad, and that is, I decided that, by weird logic, right? I decided now that I need to use a diffraction meter in order to measure the contents inside that system. There could be something else way easier, right? That I never thought of. Never thought of it, right? Maybe there's something in the image. Maybe the labels were different and I didn't notice, right? Maybe there was a little thing in the contents that said what was on there, and I didn't pick that information out. I didn't generate that feature. I didn't pull that feature in and hand it to the system, because I didn't notice it. I didn't think about it. I didn't see there being a potential differentiation. So instead, what I'm going to do is I'm going to take the natural world, and I'm just going to hook the sensor up to the end of the system, right? This is the raw input of the natural continuous world. These are sensing devices that hook up and measure the characteristics of the output performance in an image space, for instance, that would be the pixels of your CMOS, right? Of your sensor on the actual camera sensor. The individual pixels picking up light coming in. Now, how does that work? How would that be effective at understanding the world, right? Isn't it the things that characterize and make up the object, like aren't those weird shapes and complexity? Yeah, they are. But how we see it isn't the only way for it to be seen. There are statistical norms between the relationships of elements that we would not pick out because we don't think about them, because many of those processes run back here in the back of the brain, okay? The brain has a whole structure that's designed to just picking out horizontal and vertical lines, curvatures, axes, gradients of color, right? So since we have systems that describe it or that work with it that are hardware, these are hardware systems, technically we're just modeling that hardware feature extraction system that's happening in the optical region of the brain in silico, right? We're creating the system to allow the system to do what is called here automated feature extraction processes. The classification framework remains the same. Classification framework at the end is still usually a fully connected network using stochastic gradient descent. But the process in front of it that is effectively the substitute for the feature extraction engine, which is the human interfacing in between the input of the continuous natural world and the input of the neural network, right? We're replacing it now with a sequence of other networks of another type. We say that in practice, machine learning is a good chunk of this, describing your data with features the computer can understand, right? Most of it. And then a tiny bit of over here is the learning algorithm, okay? You know what I'm saying? The workhorse, the lion's share of the work is domain-specific information that requires you to understand what you're looking at. Think about medical data. Do you know enough about medical data to go and like figure out what tests to run on someone such that you can create a good classification algorithm whether or not they got the disease? No, that's the doctor. So the doctors and communities of doctors have to come together, write papers, publish information, create domain-specific knowledge for us to be able to figure out which tests need to be run so that we have the right data set so that we can do our little thing over here on the right-hand side, okay? But what did we do? We said, hey, we don't need you anymore, doctors. We're going to create a new way. We're going to digitize you, okay? No, we did this kind of. But the difference between these two things is between what is called shallow and deep networks. This is where that term deep learning comes from. If you ever wondered what that means, this is it. Now, there is no unified definition of what the word deep means. However, I have recently come across 7 being sort of a magic number. Okay, I'm not really sure why, but I think that's the number that people have sort of applied on. If we had to pick a point at which the network goes from being shallow to being deep, it's about 7 layers.
Or were they
right?
just playing craps?
It is. It could be. Yeah, it could be just, yeah, could, you know, it not greater than, but not less than or equal to 7.25, you know, like I don't know, it's weird, you know, it's from unit to probability, like the likelihood of this network being deep, okay? Shallow network is what? Wide, because you need more informational characteristics in it. So you can have a network that has multiple linearities. The more linearities you have, effectively, the more detailed the surface of the delineation is with respect to dimensionality. So a 2-dimensional system with relatively high structural complexity will be easily disseminated by a single hidden layer with enough neurons within that hidden layer in order to describe it to that degree of spatial complexity, right? So the more you put in here, the better, the smoother the transitions get along the edges of the surfaces of the composite when you recomposite them together towards the outputs. We all know what this did. We watched this happen intuitively with the TensorFlow model, right? So we said we made it wider, it got smoother, right? Because it's more individual little jagged edges, right? You could draw a circle with, you know, 1 centimeter lines, or you can draw them with like 1 nanometer lines, right? It's just each one, how precise that gets, right? How small that surface gets, how smooth the transition is. The deep system does what? It's the bucket chain, right? I get some features. I don't need a ton, but I get a few. And then I hand you my features. You're going to find features in my features. You're going to hand your features to that person, and likewise and so forth, right? So I extract what I think is interesting, and then I give I give my input to the other people behind me. They take out of my input and everybody else's input on the layer before me. They find their features through the consensus of that group. And by this process, we get further and further abstracted from the original input space, right? So the original input space is continuous natural world, and then the output of that system becomes an abstraction of representation. I now understand how features interface with respect to other features within that system. So what am I talking about? How does this work? We're going to introduce it based upon the idea of image segmentation, all right? And some of the characteristics of this are going to follow on naturally when we start talking about the idea of segmentation and sedimentation in stratification, all right? Stratification is the other terminology we use with respect to the idea of trees. So trees utilize a regional segmentation process. You could do this process right here with just a tree, okay? But what am I doing? First step, raw input image. I know it's a cat because I have it labeled. So this makes it supervised, right? Now is everything in that image a cat? No. But the object of interest, the element of interest, is a cat. Let's think about it from the perspective of saying, this image, right, versus this image. Other than the animals, those images are pretty similar, right? Lots of green, lots of plant life. You know, it's going to be pretty interesting. So let's take a bunch of pictures of the sky. Take a picture of a plane flying over, take a picture of a cloud going by, right? You take those two pictures and informationally, they're going to be virtually identical except for the cloud and the airplane. So there's going to be a tiny amount of information contained within two matrices that are largely identical to one another. Okay? So when you think about it from the perspective, we're talking about the ability to discriminate between useful information versus useless information. The background of this photo doesn't matter, so only the foreground matters. So I told you it was a cat, and I tell me how you knew it was a cat. Say, oh, it's these pixels. I draw a box around it. I say, these ones, that's cat, right? Okay? The rest of it is grass, or, you know, out of focus nothingness. Right? So what we've done is we've classified, or we've correctly identified the elements that make up that particular object, and we've provided with localization. We've centered on where that object is located in the system. The next process might be doing the same thing except for with multiple objects of multiple classes within the same visual space. Notice now we have cats, dogs, and ducks. Each one is assigned a color, and then that color is used to draw the bounding box. That bounding box is an ROI, or region of interest, in that image that tells you that this submatrix, right, this is now a subset of the original set, is localized within the image in that way. Okay? I have now classified, told you what elements were there, and I've told you where it's located in the image. Those two things are really powerful, really powerful. But I want to know even further from object detection and spatial classification. I would like to see non-overlapping segments that describe where that object is and which specific pixels you decided to pick out of that particular image, right? So this is called semantic segmentation. Now I can do this either by drawing a polyline bounding box around the outside of it like I've done, or I can do this on a pixel level. Literally tag the pixels that are used as part of that image classification framework. All right, so I say I can color code them, where I say all of the pixels that are used within dog are colored blue, which they're vaguely done so here, but we have a little bit of a problem, right? And that is that the duck and the dog seem to share some pixels with each other. They've got a slight overlap. This is permissible whenever objects have indistinct boundaries, right? So we don't know where duck starts and dog stops, right? So if we just say, these pixels could be both duck and dog, we're not sure. So that uncertainty level does what? It takes away any capacity to say exactness based upon where the duck is oriented in the space. Now, the better we are at it, the higher we go in, the stricter we resolve an individual pixel level, we might create some clarity there. But what would happen? We'd likely overfit. By creating the level of precision necessary in order to have a pixel level response to the inclusion or exclusion of an image within the space might cause us to be too strict, right? Too rules based, right? We need some flexibility to be able to identify the boundary and identify the pixels. Now I say that these elements are the elements that I'm feeding into the network, into the remainder of the network, which are going to then identify it, okay? Or are going to then characterize the outputs. This is a two-way process, all right? First, we say, I have features and information. We're gonna talk about the features and information next, but that will be what we're talking about. We're gonna talk about convolution. This is the process by which we actually extract meaningful features and what those features look like, how these are put together, all right? Curvatures, highlights, directions of gradients, etc. Yeah.
How do you determine what resolution you need or how many bits you need to make an accurate?
You said the correct term, resolution. The term resolution refers to something that was used in microscopy, all right? Microscopy says resolving power. How high the magnification needs to be on the lens in order to be able to tell the difference between two organelles in a cell is its resolving power. What is the power, magnification, necessary to resolve to tell the difference between those two organelles? Okay? What's the resolution necessary to tell the difference between those two bottles? I only need the resolution that is required so that the features extracted from it are distinct enough from one another such that they create a boundary that I can tell the difference. So I actually established the minimum required resolution based upon the scale of the object, the number of pixels, and how much they overlap and intersect one another, right? Cool thing about this is you can do that at a very high level, and you can do this for multiple resolutions. And once you have an understanding of that feature at higher resolutions, you usually find it at lower resolutions, right? So many times in convolutions, we're actually starting off with kernels. They're only 3 by 3. We're looking for features in 9 pixels at a time. Right, so it's going to go down to relatively small structures. So if these images are 256 by 256 or 512 by 512, which is common, those can be useful. But modern systems are capable of doing megapixel level images. All right, so we can do like, I believe 5 megapixels is the largest one that I've seen as an actual active recurrent heat system. It takes a long time to extract the features from a very large image like that, and it takes tons of memory. And we'll see why, because once you start, each of these convolutional kernels creates its own copy of the convoluted output in the system. But we'll talk about this at the beginning of the next class. We're going to devote some time to it. You guys, we'll switch over, probably be done with this, and switch over to
Chapter 7.
additive model in chapter 7. So.
I'm gonna be going to the senior design lab.
Yeah,
I'll just be in
Just enrollment, just having an advisor confirmation of that. And it looked like in the meantime, getting all that figured out, that
how many years old? I think it's somewhere in the neighborhood of 70.
Is it? I don't know. I'll post it again.
Thank you, see you tomorrow.
See you.
Not tonight, yeah.
I'm trying, so there's a two-step process. One, I'm trying to see if I can get justification to get a room. Because right now I'm at, if I'm at 70, if I open for 10 more, I go to 80. It gives me a full class. So I'm thinking I'm going to go ahead and tell, the problem is right now I have 2 different people that are doing it. So I have my